In this class, we're only going to cover a little bit about this concept called differentials. And really, we're covering this section to talk a little bit about notation, which is going to help us when we get to the next chapter on integrals. Here's some notation that we've seen so far. We've used interchangeably this fact that dy dx means the derivative of y with respect to x. We often express that derivative as something like f prime of x. And in either case, what these values are representing is the slope at a particular point. And the slope meaning how something is changing. So we could write the derivative, if we're thinking about the derivative as being a slope. One way that we, in the past, may have written slope is the change in y over the change in x. So the new notation that we are going to look at in this section is this here, which that triangle there is the delta, so it's delta y over delta x. And when we use the triangle notation in math, what we're trying to represent is the change. So that can be also said as the change of y over the change of x. So we can use that as an approximation for the actual value of the derivative, which is dy dx. Let's say we have a function y is equal to f of x, and we want to take the derivative. And so I'll write on here the notation from before, which is we said that f prime of x is the derivative of x, and we can also write that as dy dx. So what we're going to look at in this section on differentials is the idea that you can actually split this fraction up. So if you take this, f prime of x is equal to dy over dx, in theory you could think about it as what if you multiply both sides by the change of x. And that actually gets you to this equation. So this equation is really a variation from what we know about derivatives so far. So the idea of splitting up the dy and dx is basically to say that we could look at one value. Let's say we want to look at how specifically the y is changing if we know something like already how the x is changing. Like I said, in this class we're really only introduced to this idea of differentials and we don't go in depth in the topic. And so just as a heads up, relating to our textbook, we're really going to only look at examples that are similar to example 1 from the textbook and not any of the later examples. Okay, so let's look at some examples like that. So for each of the following, we want to find dy. So notice, previous questions, we would find something like dy dx, which would mean take the derivative. And we're actually going to do that still now, but remember that if we split it up, and if you forget, you can always just rewrite this. From what we know from the notation, f prime of x is equal to dy over dx. So if you do multiply both sides by dx, then this is dy is equal to f prime dx. So basically for this first one, we're just going to take the derivative, and then we're going to multiply it by dx at the end. So dy dx is equal to, now this is just taking the derivative part, 7 times 3x squared. So we get dy dx is equal to 21 x squared. And so the last step, since we're trying to find specifically dy, is to multiply both sides by dx. So that's dy is equal to 21 x squared times dx. And that's the final answer here. The only difference for number 2 is that we're given some values to plug in so we can actually find the specific value for dy. So first let's go ahead and take the derivative. So dy dx is equal to 300. And then we can use the power rule to take the derivative of this x part. So it's going to be negative 2/3 x to the negative 2/3 minus 1 in the exponent. And I'll just rewrite it, simplifying this. and then we can multiply both sides by dx. So we get that dy is equal to negative 200 x to the negative 5/3 times dx. But now we also want to go and plug in these values, because we specifically want to know what's dy when x is 8 and the change of x is 0.05. And so we're going to go ahead and plug this in, and if you want that negative exponent, you can change that to be positive if you move it to the denominator. And you can also rewrite it in radical form, and so if you have 5/3 as the exponent, that actually means the exponent part is 5 and the radical part is 3. So that's the same thing as saying the cube root of 8 raised to the power of 5. And when you plug that in, you should get negative 0.3125 as your final answer. Okay, and like I said, we're only introduced to this idea of splitting up the dy from the dx, and we are going to continue talking about that when we look at integrals in the next chapter.